Today we're going to take a quick look at a very comprehensive mining simulation tool called MineTwin. The purpose of this demo is to show how discrete event simulations can be used as a decision support tool in mining operations. This demo forms part of an article written for supply chain data analytics. The link to the blog post would be in this description below. The demo today will specifically look at an open pit coal mine somewhere in Africa and illustrate how you can use MineTwin to answer some of the seemingly simple questions which would be near impossible to answer using traditional static decision support tools like spreadsheets or ERP systems. So let's jump right in. One of the big benefits of MineTwin is that it is a standalone Java application which could be exported to run on any of the major operating system platforms available nowadays. You can simply open up the simulation and then import any scenario file for any mine that you want to simulate. Like any good simulation model, it is completely data-driven, meaning that there is nothing hard-coded inside the model and that all parameters and input variables can be changed by changing the scenario file. We're going to have a quick look at the scenario file, and as you can see, it is a standard Excel workbook with a huge number of sheets where you can input the different parameters, the geolocations, the trucks, the mine plan, and a range of other parameters used to data drive your model. So if we import this Excel file into our simulation, I'm just going to open up this file. It's now loading up all this data inside the model. So what I really like about MineTwin compared to some of the other software that I've used before is that it's got a really powerful scenario editing tool. As you can see here, we can immediately view the map here on the right hand side. It's a very small mine with a number of lines here, which indicates the roads that they'll be driving on. We can view a whole bunch of other objects on the map. I'm not going to go into too much detail there. And on the left hand side, you can see the different truck types that we've got with a whole range of parameters that can be edited right here inside the simulation model, from the capacities, the speeds, etc. We can specify the exact number of trucks. We can have a look at their maintenance, their unavailabilities. We can add failures to them. We can set up different ore types, materials, refueling zones, dumping areas, etc. Now, what makes this really good is that you are able to then save your scenario back into an Excel file, which makes it very easy to review for even those that don't have the simulation file, or for you to export data out of some of your other systems into that Excel file and import it back into your model. So let's do a quick demo of the model to see whether the scenario that we've loaded is actually the one that we want to run. So now as we start playing the model, you can see that we can actually view the objects in the mining areas. We can click on them, we can see the trucks, the excavators, we can see their availability, utilization, the current load on the system. We can even track a little Gantt chart here at the bottom. We can completely verify and validate that the behavior of the pieces of equipment inside the scenario is as we expected. And this is great for validating your work with your client, with the mining personnel, mine managers, truck operators, etc. You can see that everything is very, very flexible in terms of the UI. You can move things around to make it easier to follow, etc. At the moment, the model is running quite fast, so that's why the trucks are able to move so quickly. Now, for every single truck, you can also click on it and you can view the logic inside of that truck, like how's the failures, how the haulage features. We are also able to view the schedule, like what was planned, what is the truck actually doing, is it loading, is it moving, is it unloading, is it currently in failure. There's also a number of cumulative flow diagrams which can be used, performance of your mine, how much of the ore has been exposed, how much of the overburden has been moved away, how much is your buffer stockpiles, etc. And these cumulative charts are very, very powerful. Okay, now that we've seen that our simulation is working, it is doing what we want to do, we are going to try and answer a very difficult question. So what we are interested today, and the question that we're trying to answer here, if you followed the blog post on supplychaindataanalytics.com, is that we are going to try and determine the number of trucks and dozers required to meet the mine plan. And then subsequently, what's the right amount of dozers that we require. Now, the mine plan is based on the output capacity of the processing plant. So the processing plant currently is the bottleneck. So we don't want to have too many or too few dozers and trucks because we don't want to starve the processing plant, and we also don't want unnecessary buffer to build up in front of the processing plant because that'll just be a waste of our capacity. So the question is, what is the optimum number of trucks and dozers? Okay, so if we have a little look at this picture, which depicts a very simple flow diagram of how the mine works, we can see there's overburden, you do some drilling, you do some blasting, then you doze away the overburden and it's removed by trucks and shovels. Then you get to the coal, and now you have to do some more drilling, some blasting and haulage, and haul away the coal with trucks and shovels. Now the question you might ask yourself is, okay, how many dozers do I require to fulfill my plan, right? And then how many excavators are required to fulfill the plan, knowing well that the excavators are used both in removing the overburden as well as hauling away the coal. And then the same thing with how many trucks do I require, right? And now these interdependencies of excavators and trucks that are used both in removing the overburden as well as the coal is the problem with trying to solve this with static calculations or any spreadsheet or a lot of the static decision support tools available. You need a simulation model or something dynamic to be able to simulate these interdependencies. And then the last question is there a buffer needed in front of your conveyor? And if so, what is the size to ensure that you never starve your processing plant? We are going to just look at those first three questions in the demo today. And how we're going to do this, we're going to set up a sensitivity analysis inside our model. So I am going to go to our views, sensitivity analysis. We're going to set a variation range. So we're going to say we want to simulate from about 4 to 7 trucks, and the dozers, let's set that between 4 and 7 as well. And then you have to set the number of replications, right? To get a statistically significant answer, you need to run these scenarios multiple amount of times. So let's say to make this statistically significant, we're going to do 10. So the total number of scenarios that we're going to be doing, so there's 4 at the top, 4 at the bottom, and there's going to be 10. So of these 16 different scenarios, there's going to be 160 different iterations that would be executing. And I'm going to start running this. And since this is going to take a while, this is the part where you go and make yourself a cup of coffee and you come back and you see what the answer is. So I'm going to let this run just for a few seconds, but we've actually completed this analysis beforehand. So I'm just quickly going to navigate there. You can see here that it's estimating that it's going to take about an hour to complete this analysis. So once we've completed the analysis, we put up a little matrix here with the number of dozers and the number of trucks. And you can see if you've got too few dozers and trucks, you are 35% behind your plan. And as you gradually increase your dozers and increase your number of trucks, we get to a point where we've got a plus 6% fulfillment rate of our plan, and this is at a 95% equipment availability. And what's really interesting here is that if you increase your trucks just by 1 truck more from 6 to 7, we actually see that we don't see the same level of improvement that we've seen with the number of when we increased the trucks previously in one of the other areas, but we actually see a decrease, even if it is just 0.1%. And this, a lot of the time, is due to the congestion that you get at the different areas inside the mine where things are now starting to wait for one another because there's just too many of them. So we know that we need to use 6 trucks and 7 dozers. So now the next question is, how many excavators do we need? So if we redo that exact same sensitivity analysis, this time we're changing the excavators from 1 to 4, because in the previous example we had unlimited excavators to make sure that they were never the constraint. Now that we've determined the trucks and dozers, we're saying, okay, we're going to increase the excavators from 1 to 4 and see where's the point where we start meeting our plan. And we can see from this little table that as soon as we get to 3 excavators, that we start meeting our plan. And whether we do 3 or 4, right, that's buffer capacity that we can install inside the mine. Okay, thank you so much. That's it for the demo today. The links to MineTwin will all be in the description below.